So yeah, hello everyone. My name is Lokesh. I'm a fifth year PhD student at University of California, Santa Cruz. And yeah, thanks for this opportunity to present my work. And during the presentation, if you have any questions or need clarification, then feel free to interrupt so you can follow through the presentation. So yeah, let's get started. Sorry first. So today I'm going to talk about our recent work where we worked on enabling multi-tenancy on SSDs with accurate IO interference modeling. And we published this work at Symposium of Cloud Computing 2023. So let's get started. So first of all, why to enable multi-tenancy on SSDs, right? So in the past decade, we have observed that the capacities of SSDs have been increasing significantly. And this is evident from the graph shown on the right-hand side, which essentially shows the density scaling trend in the NAND flash devices. And this has been possible due to several technological advancements such as 3D integration, planar scaling, and multi-level cells. And because of this, today we can get multi-terabytes of SSDs in the market. And sharing such high-capacity SSDs provide multiple benefits, such as increased resource utilization, reduced maintenance cost, and it can also reduce the total cost of ownership. Now, although all this sounds good, we observed that when multiple applications are co-located on the same SSD, they can adversely impact the performance of each other. And to demonstrate this, we design an experiment where we host a PostgreSQL database on an SSD. Then we run other IO-intensive workload with the TPCH queries on the PostgreSQL database. And from the graph, you can see that as we increase the IO intensity of these neighboring application, the query execution time of Postgres queries keeps increasing by up to 150%. Now, such kind of performance degradation is not desirable by cloud providers. That's because it can violate service level objectives set by the customers. Now, to address this issue, there have been several works proposed or several approaches proposed in the past, and we highly divide them into two categories. And the first category of work suggests isolating SSD's physical resources. Now, although this approach could work well, there are few limitations to it or few problems with that approach. For example, these approaches require application to utilize specific SSD resources. And if you divide your SSD resources as such, then it essentially reduces the overall performance that the application can get, and it can also reduce the resource utilization. Further, these approaches require changes to internal structure of SSD. And usually this is difficult because device manufacturers take significant time to adopt such changes. So if you think about stream SSDs, which have been proposed in 2015-16, and we also had open channel SSDs then around 2018-19, we got, say, zone namespace SSDs, and none of these technologies we see very successful. And now we are seeing this flexible data placement. So as we can imagine, like what kind of timeline it has to integrate any new changes to these hardwares. Now, on the other hand, second category of works involves utilizing some kind of modeling technique to learn the IO interference characteristic first, and then use these models to guide the resource allocation policies. Now, this approach is easier to adopt because it does not require any changes to SSD internals. And since these approaches do not limit the application to utilize specific SSD resources, it can utilize or it can improve overall performance and resource utilization of the device. Now, we found two major limitations in the second category of work that I discussed. So the first limitation is the prediction accuracy of their models is low. That's because they do not consider important application and hardware characteristics while performing the modeling of IO interference. And second, their ML models do not scale to arbitrary number of workloads. For example, if you train your ML models to predict the IO interference of fixed number of workloads, then it becomes unusable to predict the IO interference of more number of workloads than what the ML model is trained to be. So to address these issues, we answer 4 research questions in this project. First is how SSD internals impact IO interference, then how workload characteristics impact IO interference, then what features are needed to represent IO interference accurately, and how to represent the IO interference impact of arbitrary number of workloads. Now, to answer the first question, let's look at this basic architecture of SSDs. Now, as you can see in the diagram, SSDs internally consists of multiple NAND flash chips connected to memory channels through which your data goes through. And then further, each flash chip consists of multiple planes, blocks, and pages. As we can see, inherently SSDs provide lots of parallelism. While this is true, we also see that there are a lot of shared resources that these SSDs have. And contention to access these shared resources can cause IO interference. Next is read-write amplification, which is defined as amount of data read or written by SSD as compared to requested by the application. And this can cause issue because due to physical nature of SSDs, the smallest unit of read and write inside the SSD is performed at the granularity of flash page. And if you see in the diagram on the right-hand side, if your IO request is smaller than the page size of the SSD, then you cannot perform direct read and write to these flash cells. Instead, you have to read the data first into the DRAM buffer, then either update it or return back to the device. So this additional operation adds additional overhead to serve those IO requests, and those IO requests keep these hardware resources busy. As a result, other IO requests can starve and it can affect the performance. Similar to IO size, if your IO crosses the page boundary of the flash page, then in that case, instead of performing read, modify, write operation on one page, you have to perform it for multiple pages. This makes that situation worse, causing higher IO interference. Then finally, we have read-write asymmetry. So in order to perform a write operation, SSDs have to reprogram a NAND flash cell. And usually it requires them to apply higher voltages, which makes write operations much more expensive than read operations. As a result, write operations cause higher IO interference compared to read operations. So now that we understand how SSD internal impact IO interference, next I'll show how workload characteristic impact IO interference. And in today's talk, I'll discuss the top three workload features that affect IO interference. For the remaining, please check out our paper. We have very good insights about what happens inside the SSD and what can cause IO interference there. Now, to perform this workload characteristic analysis, we devise several synthetic benchmarks using FIO, which is a storage benchmark tool. And in each benchmark, we have one workload under test and several interfering workloads. And in these interfering workloads, we only vary a single workload property, keeping all the workload properties constant. This allows us to understand how that specific workload property affects the IO interference. And to ensure that the IO interference happens, we ensure that the aggregate bandwidth of interfering workload and workload under test goes beyond the maximum device bandwidth. And as you can see on the hardware configuration, we do this analysis for two types of SSDs. One is enterprise grade NVMe SSD, and second is consumer grade SATA SSD. Now, I'll take a bit more time to explain our IO size experiment setup because IO sizes are tricky to compare. Because if you remember, our goal is to keep one property of workload constant, one property varying and all the other properties constant. Now, with this requirement, if you change your IO size, then you either change your average IO bandwidth of the workload or you have to change the IO rate. So as a workaround, instead of using one IO size, we utilize two IO sizes, as you can see in the table below here. So for aligned size interfering workload, we utilize the IO sizes of 4 kilobytes and 8 kilobytes. And unaligned size interfering workloads, we utilize the IO size of 6 kilobytes, which is average of 2. And by doing this, we only vary the IO size property of the workload, keeping all the other workload properties constant. Now, with this setup in mind, let's look at the results. So as you can see, so first of all, how to read this graph. So here, x-axis of the graph shows the average IO sizes used by the interfering workloads, and y-axis of the graph shows the delta between the bandwidth degradation happened for workload under test when it ran against, say, unaligned size interfering workload versus unaligned size interfering workload. Now, now if you can see the NVMe SSD results, so we can see that this delta is around 20%, which is significantly higher. And why this happens? This happens because of read modify write operation that we had to do in case where your IO sizes are not aligned to the page size of the SSD. Now, if you see for higher IO sizes, we see this impact going down. And the reason for that is for higher IO sizes, the ratio of aligned size IOs to unaligned size IOs keeps increasing. As a result, we do not see significant overhead for higher IO sizes. Now, surprisingly, for SATA SSDs, even for smaller IO sizes, we do not see significant delta. And the reason for that is SATA SSDs uses SATA interfaces which have significantly higher latencies. And these higher latencies makes the IO interference impact of unaligned IO sizes insignificant. Next, these are the results for our experiment for IOS offset alignment analysis. So in this case, the experimental setup is easy. As you can see on the graph, we utilize the following IO sizes shown on the x-axis, and we ensure that these IOs are performed aligned to the page offset of the SSDs for aligned offset workloads. And for unaligned offset workloads, we ensure that these offsets are not aligned to the page offset of the SSDs. Now, for NVMe SSD, the results are similar to the IO size experiment. However, now surprisingly for SATA SSD, we do see significant delta for this experiment. And the reason for that is, as I explained before, now when your IO offsets cross the page boundaries, then they have to read multiple pages. So as a result, this overhead becomes significantly higher that even SATA interface latencies cannot hide it, right? So these two experiments shows that how SSD internals are important, and if you want to model or characterize the performance of these SSDs, we need to consider them. Otherwise, it's difficult to have good, accurate performance models for SSDs. Now, next, on the workload side, I'll show you the analysis of temporal axis pattern analysis. And this is important because in real world, workloads usually do not have, say, uniform IO rate. They usually have varying IO rate. And even while being such a common use case, we did not find any of the prior work considering this factor. And now, so we want to analyze that whether this non-uniformity in their IO rate or burstiness in the IO rate what kind of IO interference impact it has. So to do that, we defined or devised two interfering workloads, one workload with uniform IO rate and other workload with varying IO rate. And in order for comparison, we ensure that their average IO bandwidth is constant. So for NVMe SSD, it's 1024 megabytes per second, and for SATA SSD, it is 128 megabytes per second. And from the results, we can see that there is significant delta between the IO interference impact caused by uniform workload versus bursty workload. And this happens because, like, if you just see the average IO bandwidth, it is significantly lower than the maximum bandwidth supported by the device. However, in case of bursty workloads, there can be phases where your required IO bandwidth goes beyond the maximum bandwidth supported by the device. So in that case, it increases the contention for workload under test significantly, showing this kind of behavior. Now, there are two takeaways from this experiment. First, burstiness can have different IO interference impact compared to uniform workload. And the traditional metrics such as average IO bandwidth are not the right metrics to represent this. So how do you represent the burstiness of the workload? To do that, we propose to use standard deviation as a proxy to represent burstiness. And to analyze its applicability, we further divide several synthetic workloads with different variability. And from the graph, we can see that the standard deviation of interfering workloads, which are shown on the x-axis of this graph, nicely correlates with the performance observed by workload under test. So this shows that we can use standard deviation as a proxy to represent the burstiness of the workload. I think my slides are messed up, but yes. So now that we understand how both SSD internals and workload properties impact IO interference, next is how do you represent them so that you can model IO interference accurately. And here we propose our gray box features. And the slide or the features listed on the slide are the features that we propose, which covers both SSD IO interference impact caused by SSD internals and non-uniform workload properties such as burstiness. So as you can see, we propose to categorize the IO traffic first according to read and write to consider read-write asymmetry in the SSDs. Then further, we categorize them according to their IO sizes, that is aligned versus unaligned IO sizes. This considers our read-write amplification issue. And then we do take the weighted mean IO size to represent all the IO sizes because workloads can have varying IO sizes. And then to consider the internal device parallelism, we utilize IO depth, average IO rate, and IO bandwidth. And to represent the temporal IO access patterns, we utilize standard deviation and average values of bandwidth. And finally, to consider the spatial IO access patterns, we utilize unaligned offset ratio and random offset ratio. So now that we know what features to use, next question is how to support predictions for arbitrary number of workloads. Now, to understand this problem, first, let's look at this use case. Suppose you train your ML model to predict the IO interference caused by a few fixed number of workloads. Then in that case, this ML model will fail to predict the IO interference for higher number of workloads. Now, in order to support arbitrary higher number of workloads, if you increase your feature space significantly, then you end up in curse of dimensionality problems. So in that case, your training ML model itself becomes difficult because we don't have that kind of data, and generating this kind of data can be very expensive. And so to address these issues, we propose gray box feature aggregation technique, where we aggregate the features from multiple number of workloads without losing their IO interference characteristics. With this, we make sure that our ML models have fixed number of features, so their training becomes easier. And while doing that, we also support the predictions for arbitrary number of workloads. Right. And these are the equations that we utilize to aggregate our features. So equation 1 is used to aggregate the weighted mean sizes of the workloads. And then equation 2 and 3 are utilized to aggregate the average and standard deviation values, this is kind of how you aggregate the normal distributions. And then the equation 4 is used to aggregate different types of ratios, that is unaligned offset ratio and random offset ratio. So now that I have discussed our overall technique, next I'll show you our evaluation. And here is the evaluation setup that we use. So we utilize traces from two real-world cloud providers, that is Alibaba and Tencent. And you can find these traces on SNIA website. And we also create our own synthetic traces so that we cover a variety of use cases or different aspects of workloads. Then on the ML model side, we utilize random forest regressor algorithm, which is found to be the best model by the prior works. And we concur with their analysis because in our analysis as well, we found that random forest gives better accuracy compared to other models. And we compare our technique against weighted mean aggregation technique. So this aggregation technique has been proposed for hard disk drives, but we didn't find any of the work which proposes this technique for SSDs. So we utilize those. And one major difference between this and our technique is that so weighted mean aggregation, we only use the newly proposed gray box features. We utilize traditional features. And then we evaluate our approach on two metrics. One is R2 score, which is coefficient of determination. So essentially what it shows is the proportion of predictions that fits well with the actual values. And mean absolute error is a measure of accuracy. It basically shows how far we are from the actual value, our predictions. And table on the right-hand side, the feature represents the dataset format. So as you can see, we utilize gray box features for workload under test, then aggregated gray box features for all the interfering workloads. And then we predict the absolute performance for workload under test on 5 performance metrics. That is average bandwidth, average latency, 90th percentile latency, 95th, and 99th percentile latency. So now that we understand our evaluation setup, let's look at the results. So first, I'll show you our results for synthetic workloads where we performed the feature sensitivity study, essentially to see how these gray box features helps us to improve the accuracy. And here are the results. So this graph shows the R2 score for predicting the performance of workload under test for 5 performance metric. And x-axis shows all the performance metric that we predict, and y-axis shows the R2 score. So overall, from the results, you can see that we start from weighted mean, where none of the gray box features are used. Then we add first the offset related features, and you can see that the accuracy has improved there because of that. Then we add size, and then the burstiness related features. So we can see that while we add these features and then check the accuracy for each added features, we see some kind of improved accuracy or R2 score. And just a note here, R2 score is like higher the better. So we can see that for gray box features, we have highest R2 score. Then on this graph, this graph shows the mean absolute error normalized to gray box predictions. And here we see similar trend, even in the absolute performance predictions. And here the prediction can be, as you can see, can be better from say 2x to almost 14x. So we reduce the mean absolute error by that many times. So next, I'll show you the results for our real world workloads. Here we completely remove all the synthetic workloads and just utilize the real world workload traces obtained from Alibaba and Tencent. And here are the results. So as you can see, for real world workloads, we compare our technique against weighted mean, and this graph shows the R2 score. And from overall results, we can see that the R2 score of weighted mean is like always less than 0.8, where R2 score for gray box is greater than almost 0.97, so which looks pretty good. Then further, taking the mean absolute error, and here also we can see that our gray box outperforms weighted mean by 4 to 12x lower mean absolute error. And so this happens because of the same reason that the traditional features do not or cannot represent the IO interference impact caused by SSD internals, and they also do not consider the non-uniform workload properties such as burstiness. And they end up only using, say, like average bandwidth as a measure to represent the IO traffic, which cannot predict the other aspects of the SSDs and workloads. So now here I will show, or this graph shows how exactly the improved accuracy of ML model like helps with, say, avoiding SLO violations or reducing the resource utilization. So first of all, how to read this graph? So here the x-axis of the graph shows the randomly 30 random samples from our predictions, and y-axis of the graph shows the prediction error. And so, and the black dotted line here shows the SLO, which is 10% in this case. So what does it mean? That your tenant is not willing to accept any performance degradation or variation beyond 10% of the actual performance that they should get when they run on a single SSD without any other neighbor. So with this, as you can see, in case of positive predictions error, if your model becomes too optimistic and gives some kind of positive prediction error, then you can pack more workloads onto the same SSD. But in that case, it can lead to SLO violations because of these wrong predictions. On the other hand, if your model becomes too pessimistic and gives you negative prediction error, then it prevents you co-locating more applications on the same SSD, which can lead to low resource utilization. So this is the green area where we want to be, and which can, so we want our predictions to be accurate for this 10% of delta, where we can achieve high resource utilization without SLO violation. And from overall results, we can see that gray box always performs or keeps the prediction error within the 10%. And on the other hand, weighted mean features almost for 80 to 90% causes wrong predictions, which can lead to low resource utilization or SLO violations. Now, further, to further evaluate how exactly it can, or how much it can help with the increasing resource utilization, we built a simple resource allocator. And this slide, this diagram shows the usage model of how our resource allocator can be used in the real world. So as you can see, in the typical data center environment, we get the workloads to schedule. And if we know if we know that workload, that is the features for that workloads are known, then we can directly use our gray box resource allocator, which utilizes the ML model and can place your workload on the SSDs. In case if you don't know your workload, then we place them on the staging SSDs where the trace collection for that workload happens. And once we are able to extract the gray box features, then we can check with the gray box resource allocator and then either move the workload to these SSDs, or virtually we can just move this SSD in this finally allocated SSDs. Now, this slide shows the results of our resource allocator. So we compare our resource allocation efficiency with two baselines. One is quota-based baseline, which is traditional method to provision the SSDs in data centers. Basically, they use worst-case interference as a measure to avoid or to co-locate workloads onto the same SSD. And second is weighted mean. So weighted means resource allocation logic is similar to gray box. The only difference is they utilize ML models that are trained with the traditional features. So now, first of all, how to read this graph? So x-axis of the graph shows the service level objectives, level of service level objectives that needs to be supported. And y-axis of the graph shows the number of SSDs that are needed to accommodate 1,000 workloads. Now, from the results, we can see that when your tenant is not willing to accept even a single % of performance degradation, then none of the techniques perform, or all the techniques perform the same. And the reason for that is there is always some kind of performance fluctuation that SSDs can have even without any other workload, such as, say, garbage collection happens, and in that case, you are bound to see lower performance. Then, on the other hand, if you relax your SLO to say 5%, then we can see that gray box can accommodate 1,000 workloads within, say, 3 or below 350 SSDs. As you can see, this as compared to other technique that is weighted mean or quota based, they require more than 600 SSDs. And this shows that our having accurate IO interference prediction can significantly reduce the number of SSDs that are required. And so, yeah. So in conclusion, we proposed a gray box feature representation and aggregation technique that helps us to improve the modeling accuracy of IO interference. And these accurate models can further help us improve the resource utilization while preventing or supporting tenants SLOs. So yeah, that's it from my side. Thank you for listening, and I can take any questions if you have. And this QR code, if you are wondering, that is the link for our paper. So if you are interested, you can check it out as well. So yeah, thank you.